Dear students, in the previous episode, we have discussed on the atmospheric temperature, insolation and global energy budget. This episode focuses on the horizontal and vertical distribution of temperature. The present episode consists of the following modules. The first one deals with horizontal distribution of temperature, prominent controls of temperature, and seasonal distribution of temperature, and vertical distribution of temperature, and finally temperature inversions. In the previous episode, we have discussed about the different processes of heating and cooling of the atmosphere. The temperature of a place depends on the amount of insolation received there, which is determined by latitude. Besides latitude, there are other important geographical factors of the distribution of temperature. Isotherms are commonly used to show the horizontal distribution of temperature. We know that the temperature decreases with altitude at the rate of 6 degrees Celsius for every 1000 meters. Horizontal distribution of temperature. There are a number of factors that determine the horizontal distribution of temperature. There is a general decrease in temperature from the equator towards poles. The isotherms over certain part of the globe are closely spaced, while elsewhere they are widely spaced. There are other factors also affecting the distribution of the temperature, like differential heating of land and water, effects of ocean currents, mountain barriers, etc. The highest temperatures are found in the tropics and subtropics, which receives the highest amount of insolation all year around. On the contrary, lowest average temperatures are recorded in the polar regions. Isotherms are the lines joining points of equal temperature. Global temperature patterns are shown with isothermal maps. The temperature maps are based on daily averages. Isotherms, while passing from the continents to oceans, get distorted. The distortion is larger in the northern hemisphere due to the large percentage of land surface. The coldest temperature is in the winter, and the highest temperature in the summer are found over continents. Since the temperature do not fluctuate as much as over water as over land, the north-south migration of isotherms is greater over continents than oceans, especially in mid-latitudes. The temperature gradient is very steep in the higher latitudes as well as along the eastern margins of the continents. Now, let us see the prominent controls of temperature. Gross pattern of temperature are controlled largely by the following 4 factors. Temperature responds sharply to altitudinal changes. Isotherms on world temperature maps have conspicuous east-west trend. If the earth had uniform surface and did not rotate, isotherms probably would coincide exactly with parallels. The fundamental cause of temperature variation would over in insolation, which is governed by primarily on latitudes. Summer temperatures are higher over the continents than over the oceans. The isotherms over the continents bend poleward. Winter temperatures are lower over the continents than over the oceans. The isotherms over the continents bend equatorial world. In both seasons, isotherms make greater north-south shifts over land than over water. Regularity of isotherms pattern in the mid-latitudes of the southern hemisphere is a manifestation of the fact that there is a very little land. Isotherms in near coastal areas of the oceans have prominent bends where warm or cool currents reinforce the land-water contrast. Cool currents deflect isotherms equatorial world. Warm currents deflect them poleward. Cool currents produce the greatest isothermal bends in the warm season, warm currents in the cool season. Isotherms reflect the changing balance of insolation, moving northward from January to July and southward from July to January. Isothermal shift is more pronounced in high latitudes than low latitudes and over continents than over the oceans. Temperature gradient is steeper in winter than in summer and over continents than oceans. The coldest places on the earth are over land masses in higher latitudes, for example, Siberia, Canada, Greenland in January and Antarctica in July. The highest temperature are found over the continents in subtropical latitudes where descending air maintains clear skies, not in equatorial regions where frequent cloudiness prevent highest temperatures. For example, northern Africa and southeastern Asia and North America in July, Australia, southern Africa, South America in January. Highest average annual temperatures are in equatorial regions because these regions experience so little winter cooling. Now let us see the average temperature range. Difference between the average temperatures of the warmest and coldest months are usually, but not always, in July and January. Largest annual temperatures ranges occur in the interiors of high latitudes continents. Annual temperature ranges in the tropics are very small. Now let us see the seasonal distribution of temperature. Since January and July represent the seasonal extremes, the horizontal distribution of temperature in these 2 months only is described. Distribution of temperature in January. If you look at the January map, it is quite evident because of the presence of the more land surfaces in the northern hemisphere. The isotherms are more regularly and closely spaced. On the contrary, in the southern hemisphere, because of the large water surface, the isotherms are relatively more symmetrical. The northern hemisphere has large number of isothermal lines than in the southern hemisphere. Isotherms bend sharply in January towards the equator. In January, the coldest places in the earth is found in the northeastern Siberia and another coldest region lies in Greenland. In the mid-latitudes, the western coastal regions of the continents are warmer because the prevailing westerlies. In the northern hemisphere, the isotherms deflect more towards the pole because of the warm current. There will be a larger contrast in the temperature over continents and oceans in the northern hemisphere. Distribution of temperature in July. Isotherms in July in northern hemisphere are most irregular and zigzag. On the contrary, the isotherms in the southern hemisphere are more regular and straight. Higher temperatures is seen in the northern Africa through Southwest Asia to the northwestern part of United States. In northern hemisphere, the continents are much warmer than oceans. There are less number of isotherms and they are widely spaced in northern hemisphere. Isotherms over continents bend towards the North Pole and over oceans towards the equator. Annual range of temperature. The difference between the warmest and the coldest monthly means is called the annual range of temperature. It varies from place to place. The following are the factors that affect the control the range of temperature. The first one is the latitude. The second one is the height above mean sea level, ocean currents, prevailing winds, precipitation and cloudiness, local relief, distance from the sea. So, now let us see the latitude. Twice the year the sun rays are vertical at the equator. Thus, the temperature is uniformly high in equatorial regions and annual range of temperature is negligible. But from equator to poleward, there is a decrease in temperature. It results in greater range of temperature. In polar regions, the length of the day and night is about 6 months. One should expect the highest range annual temperature, but due to the angle of incident is low and most of the energy being reflected back checks the rise of the temperature. But in mid latitudes where seasonal variation of temperature is greatest, the annual range of temperature is also greatest. Height above the mean sea level. The annual range of temperature at a particular place is highly controlled by height. At high elevations, the rarity of the air, large amount of precipitation and cloudiness combine together to lower down the average temperature. Thus, places situated at higher elevations have lower annual range of temperature. Ocean currents. The warm ocean currents, prevailing winds help to rise the temperature of the adjoining regions. The effect of warm ocean current is more pronounced in winter. Hence, the annual range of temperature is relatively smaller. Prevailing winds. Along all the factors that have controlled influences over the annual range of temperature, the prevailing winds are the most important aspect. Offshore winds bring some increase in annual range of temperature of the adjoining land. Besides, the effect of ocean current is largely determined by the prevailing winds. Hence, the annual range of temperature is relatively low. Precipitation and cloudiness also play a very important role. In those regions where the rains are more and the skies are covered with clouds, the summer temperature are not allowed to fall much. Thus, the annual range of temperature is relatively low. Local relief. Slope is one of the most important factors which affect the temperature of a place. Slopes facing the sun have higher temperature during summer, and the slopes protected by the sun have lower temperature during winter. Thus, the local factors are also affect the annual range of temperature. Distance from the sea. Water is heated or cooled in a longer period of time than land. Because of these characteristics of water, the coastal areas enjoy moderate climate and the variations in temperature between warmest and coldest months are not very large. Increasing distance from the sea coast, there is a corresponding increase in the seasonal variations of temperature. Hence, the annual range of temperature is very, very negligible. Let us see the vertical distribution of temperature. As one moves from equator to poles, there is a steady decrease in temperature are observed. In the same way, there is steady decrease in temperature with increasing elevation in the atmosphere. This decrease in temperature with increasing altitude is called vertical temperature gradient. Various factors affecting the vertical temperature gradient interact in a complex manner. Energy transfers involve the latent heat of condensation, cooling of air by the process of radiation, and heat transfer from the ground. High pressure systems descending of air, which lead to warming of extensive layer of air, results in the decrease of vertical temperature gradient. On the other hand, low temperature systems give rise to ascending of currents, increases the vertical temperature gradient. Moisture is said to be the additional factor which creates lot of complications in the vertical distribution of temperature. Lapse rate. The vertical decrease in temperature is called lapse rate. The lapse rate is not constant, but it varies with height, location, and season. Vertical decrease in temperature continues to only up to the tropopause, beyond which it stops. In tropical regions where insolation is intense, the lapse rate is generally high, up to 160 meters on most of the afternoons. The lapse rate may be steep or slow depending upon the atmospheric conditions. Heating of the lower air is not due to the nearness of the earth surface, but at the lower level air is denser than the upper layer containing large quantity of water vapor and dust particles. On the contrary, the upper strata are dry, fewer amounts of water vapor and carbon dioxide are present. Upper air is more transparent, temperature is relatively low, hence the temperature is low as we go away from the earth's surface. Actual lapse rate and annual lapse rate is always different. Continents and oceans not only influence on horizontal distribution, but also on the vertical distribution too. Under normal conditions, the temperature decreases with altitude, but sometimes the temperature increases with altitude also. This phenomena is known as temperature inversion. During winter in polar regions, layers of the air close to the surface become so cold that up to a certain height the temperature increases with elevation. Outside the polar region, the inversion of temperature over continents is of common occurrence. But on oceans, inversion of temperature occur in summer. Another important feature of lapse rate is that in tropical regions, the decrease in temperature with elevation continues up to a height of 16 to 18 kilometers in the troposphere. So, in this zone, the temperature at the outer boundary of the troposphere is reduced to minus 80 degrees Celsius. But in polar regions, the lapse rate continues up to 6 kilometers. Beyond latitude 60 degree north and south, the highest of the troposphere is 10 kilometers in summer and 9 kilometers in winter. The height of the troposphere in highest latitude is relatively less. temperature inversion. In the lower part of the atmosphere, up to the height of 8 to 10 kilometers from the Earth's surface, the temperature normally decreases with increasing altitude. It's about 6.5 degrees Celsius per kilometer. But sometimes under special circumstances, it is reversed and temperature instead of decreasing is found to increase with elevation. In other words, the temperature gradient is inverted. It is called inversion of temperature. Temperature inversion near the surface may be produced under the following conditions. When there is a long clear winter nights, clear sky with clouds, dry and calm air, the inversion of temperature occurs. When there is a little wind movement near the ground or wind movement is too slow, little mixing of air, inversion takes place. In higher latitudes, snow covered areas where solar radiation is reflected, loss of heat, air near the surface goes rapid cooling. Temperature inversion develops. In polar regions, temperature inversion is common all the year around. Snow covered land surfaces in temperature regions witness temperature inversion at night in winter. Inversion layer in polar regions is thicker than middle latitudes. It is greater on the continent in winter and on oceans in summer except in Arctic Ocean. During winter, there is a balance of temperature inversion. Now let us see the type of inversion of temperature. Radiation inversion, subsidence inversion, trade wind inversion, frontal inversion. Radiation inversion. The surface inversion produced by radiational cooling of lower air is called radiation inversion. Inversion layer develops at an altitude of about 90 meters. Since the land surface radiates more heat than the air, ground is cooled more rapidly than the air at a great height during night. With the result, the coldest air lies at the ground and is overlaid by warm air. The layer of air in close proximity of the Earth's surface is cooled by the process of radiation and condensation more quickly than the upper layer of the air. Thus, at a certain height, it's about 90 meters, the temperature increases with the altitude. It continues up to 300 meters. Subsidence inversion. Subsidence inversion takes place in valleys and mountains. When air blows over the hills, it is heated as it compressed into the side of the hills. When the warm air comes over the top, it is warmer than the cooler air of the valley, also increasing the inversion. As the air comes over the top of the hill, it causes the air in the valley to be compressed, heating the cooler the valley air from the top down. It is known as subsidence inversion. The temperature inversion usually present in the trade wind streams over the eastern portion of the tropical oceans. In the equatorial zone and over the western portion of the trade wind belt, the inversion does not exist as a mean condition, although it appears in certain weather patterns. The strength of the inversion varies enormously, occasionally being more than 10 degrees Celsius over 1 kilometer, but sometimes being absent altogether, especially in the northern hemisphere. The inversion is generally strongest when the highest of its base lower and vice versa. The thickness of the inversion layer varies from only a few meters to more than 1000 meters and an average thickness of about 400 meters. Frontal inversions. Frontal inversions are inversions caused by a shallow cold front blowing in under warmer air. In other words, sometimes bunch of cold air called an air mass will get blown by the wind from one place to another. Warmer place and will get blown underneath, the warmer air causing an inversion. This is known as frontal inversion. Now, let us see the effects of inversion. So, one of the most harmful effects of inversion is that trap the pollution close to the ground, trapping the smoke. In places like Los Angeles and Salt Lake City, there is a real problem because of all the emissions from vehicles, power plants and other factories or heat sources add to the atmosphere. Besides, inversion also traps sound waves. Because of this, loud sounds coming from airplanes while taking off will seem louder as the sound waves refract from the inversion layer and back down to the ground. But sound waves are not the only thing that gets refracted by weather inversions. Light can be bent in inconsistency of the temperature. To sum up, during the revolution of the earth around the sun, the inclination of the axis remains the same. Therefore, all its positions are parallel to each other. Sun is a primary source of heat, but it is not the rays of the sun which directly heat the air. A considerable portion of heat and light is absorbed by the atmosphere, but the increase of temperature is small due to the great mass of air. The earth emits infrared rays after receiving the heat energy from the sun. Consequently, the air absorbs a larger portion of heat radiated out of the earth. Normally, the temperature goes on declining as we proceed higher up from the sea level, but under special circumstances, there is the increase in temperature with an increase in elevation. This state of affair is known as the temperature inversion. The isotherms near the equator bend polewards over the land, equatorward over the sea towards the pole. The bends are in the opposite direction. The horizontal distribution of temperature depends on insolation, seasonal changes, winds, currents, and nature of the land. High pressure systems descending of air, which lead to warming of extensive layer of air, results in decrease of vertical temperature gradient. On the other hand, low temperature systems give rise to ascending of air currents, increase the vertical temperature gradient. Apart from temperature, air pressure and wind are also influenced on the other elements of the weather, which we will be discussing in our next module.